In this video, we'll begin to use definite integrals to compute volumes. Here we have the graph of a parabola given by the function f of x equals the quantity 1 minus x times the quantity x minus 6. Let's look at the region in the first quadrant cut off by that parabola and shade in that region. Now let's let this region be the base of a three-dimensional solid. Let's slice this region perpendicular to the x-axis, or parallel to the y-axis, and above this little slice, let's build a square. So that when we look at this object in 3 dimensions, a slice perpendicular to the x-axis will be a square. Depending upon where we put that slice, the square may be very big, or smaller, or very small. What would the object look like that's created by putting together all of these square slices? We can create a frame that all of these squares fit into. Our next question might be, what is the volume of this three-dimensional solid that we've created? It fits inside a rectangular box that is 5 units by 6 units by 6 units tall. So its volume has to be less than 180 cubic units. It turns out that we can compute the volume of this object without actually knowing what it looks like. All we need to know is what the base looks like and what one of these slices looks like. Here's our function, f of x equals 1 minus x times the quantity x minus 6, which we can also write as negative x squared plus 7x minus 6. If we didn't already have a graph of this parabola, we know that it must pass through the point where x equals 1 on the x-axis and where x equals 6 on the x-axis. We know that it must point down, so it must look something like this. This region is the base of our three-dimensional solid. We can then sketch in a representative slice, or where that representative slice intersects the base of the solid. If we draw that slice separately, we get a square object that is delta x units wide, the thickness of our slice. What are the dimensions of this square? The base of the square is the same as the length of this slice, which extends from where y equals 0 up to where y equals our polynomial function. So one side of the square is the quantity 1 minus x times x minus 6 units long, when our slice is x units from the y-axis. Because this is a square, the cross-sectional area of the square will be the square of the side length, and the volume of this little x slice will be the area of the square, since I'm squaring this, the sign doesn't matter here, times the thickness of the slice, delta x. If I add up the volumes of all of these little slices, I get a sum that approximates the volume of our object. This is a Riemann sum. And this Riemann sum converges to this definite integral. The limits are from x equals 1 to x equals 6, because to get every possible slice, we must integrate from x equals 1 to x equals 6. The integrand is simply a polynomial, a 4th degree polynomial, and if we expand this polynomial, we can integrate it without much difficulty. The algebra is a bit messy, so I'll leave the details to you, and check that the definite integral should work out to be 625/6, or approximately 104.17. And we note that this is in fact less than 180, which is the volume of the rectangular box that enclosed this geometric solid. Although we've created a three-dimensional graph of our object here, once again, we don't need to do that to find the volume of such objects. All we need to do is graph the base region and draw a representative slice, then sketch the cross-section of that slice and determine its cross-sectional area. In our next video, we'll examine other types of three-dimensional solids whose volumes we can compute using definite integrals.